all that crazy, we might actually be able to, the more I look at my notes and stuff, I think we'll probably be able to get through chords in a day and then spend more time on inscribed angles and things like that. So when I'm looking at this here, we're talking about this thing called a chord. Now, a chord, like we find on Monday, a chord is a segment that's in the circle that has endpoints on the circle. And what happens here is that you get this idea of chords are generally labeled as segments. So CD in this case would be what we would call a chord. We had a problem, I think it was yesterday. I showed you that quick example where you had to work with the angles. And what happens a lot of times with chords is that if you draw a radius to the endpoints of your chord, you're generally going to find that you create isosceles triangles. Okay? A lot. That happens quite often. And you saw that last night on a couple of those homework questions where it asked you to find the missing interior angle of one thing and so on. It was always creating these things. Now, what we talk about here is this thing called chord. The chord CD, segment on the or in the circle, endpoints on, and then this is what we call its intercepted arc. So CD is the chord, CD is the intercepted arc. It's the arc that has the endpoints CD, basically, and we've talked about that before. Which of those two segments would be longer, the chord or the arc? Why, Josh?
Because like it's covering the same distance, but it's like because the straight line is the fastest.
Correct. Because remember, the chord is the portion of the circumference, which means you had to have that arc length thing to it. Ooh, arc length. Huh. Maybe we should revisit that as well because it's going to show back up.
Oh my.
Go figure, right? Arc length, just in case we all forgot, because I'm sure that would never happen, right? Well, you're right, but there was also a formula for it. Arc length. Arc length is on your formula sheet that you guys all have. It's something that we use pretty regularly, and it also happens to be something you guys make mistakes on pretty regularly. Remember, your arc length is always going to be the measure of the central angle over 360 times 2 pi r. And that's going to be the arc length. So in order to determine the length of an arc, you have to know angle and a radius. And remember, we've dealt with that before where you were given the arc length and an angle, you could find the radius, or you're given the arc length and the radius, you can find the angle. Because if you think about it, if you have circumference, if you think about it, what you're looking at there is you've got three possible variables, if you will. The arc length, the angle, and the radius. You only need 2 out of the 3 to solve for the third. So it is a very, very common thing that they kind of intertwine a lot of this stuff. Like we were saying yesterday, geometry, especially within circles, it is a hodgepodge of things that you have seen in the past. You just would rather not have to see them again. It's the unseen scene. See? I'm going to continue on because I don't know what I'm talking about. Lofthouse picked the card correctly today. We started talking about combinations and things like that. So he walked in, said, "Yo, factorial, and what card is this?" And he said, "Ace of Spades." Video. Not. Yeah, it was crazy. We don't want to know. No, we're busy. We talked about these before as well. You guys remember the difference between a major and a minor arc? They just kind of come back in with the vocabulary. Last chapter we defined it. We didn't really have a lot of problems with them. But do you remember the difference between a major or a minor arc? Please do that.
It's like a major arc will be
Elaborate. I think you're close. You're close-ish.
Very similar. What are you gonna say? What?
Major are above 180, minor are below 180.
And that's kind of where you were going towards. And that's and you. No, you weren't sounding stupid. I appreciate you trying it out, and that's good. Like you said, going out on a limb. I appreciate it. Now, what happens if the arc measures 180? What's that called?
Semicircle.
Very good. So the major arc is an arc that is greater than 180 degrees. The minor arc is an arc, that's less than 180. If an arc equals 180, it's called a semicircle. Okay. When you had these labeled, do you remember how many letters we used for major more often than not?
Uppercase letters.
Well, yes, they're uppercase letters. Thanks. Yes, ma'am. Yeah. A lot of times with major arcs, we would use 3 letters. So if I say A, B, C, so arc A, B, C would be considered a major arc because it's larger than 180 degrees. It also tells you direction. Yeah, Josh.
What if like the arc, so what if the 3 arcs make like 360? That's still like what can you consider a major arc?
If the 3 separate arcs add up, oh, that just means that if this is a 60 degrees, I'm sorry,
Like if they connected to
so it'll be 120 that goes full circle. Well, if it's 120 degrees, is that a major or a minor arc? It's minor. But if I put 2 of them together, it would be major. Okay? It would just be a circle. Okay? All right. So remember, the lettering tells you direction. Start at A, you're going to end at C, but it tells you to go through point B. That's different than just saying arc AC. Arc AC just means the shortest distance between the 2 points, not the straight line, because it's on the curve. Okay? And that's why they label it as such with the little curve over the letters. Okay? That vaguely ring a bell. I know it's been about a month or so since we looked at this, but we talked about this before. I just want to re-emphasize a few of these parts, you know, that it was vocabulary. So, you look very worried. You can stand up and dance if it wakes you up. Well, softball? Did you get hit in the head? We had our son, obviously I've said this, he plays baseball, and I'm not coaching them this year, but I was helping out, and one of the kids, we're trying to teach the kids some proper form for catching. And I caught for a long time in Little League and minor, you know, all the stuff going through. So I'd help out a lot of the catchers and the pitchers with form and just simple move and all that. And one of the kids was really afraid that the catcher's mask that he had, the ball was going to get between the eye spots. He's like, no, I'm going to get hit in the head. It's going to go over there and hit me in the face. Like, no, well. So I took the ball and I'm like, well, just hold the helmet, not in his head. And I hold the helmet and said, see, look, it's not going to hit me. I don't know. But so he was kind of timid about it because we're trying to get kids comfortable and to try things, and we're trying to learn what kids are better at what spots. As we go throughout the season, we'll place kids in better positions, you know, to help us win. So the one kid he was playing on, I think it was our scrimmage the other day, and he's sitting there catching and all that, and he got a foul tip right into the mask, right in the middle spot there, and he knocked him over, and he got up, and I'm like, see, I told you it was going to go through, hit me in the head. And he starts laughing. He's like, yeah. And then next you know, next ball, another foul tip, and it hits him right square in the gut. He goes, oh, and he falls over again. Like, you're doing great. You're doing great. Yes, sir.
That kind of reminds me. So I was playing
Gosh.
football with my friends, and somehow the football I thought it was going to go for my gut, but it went lower.
Oh, that's always fun. Anyway.
Where it was practice and we're taking fly balls in the outfield because we were going to it's really high fly ball. Frank was run at me, and it's fast enough to just run. It goes from center field all the way to near second base.
Yeah.
Dies or it goes back, just hit me right there, like dead center.
knows I was coaching first base this weekend, and there was a screaming line drive, and I just ran over to try to stop it with my foot. The last second, it bounced and hit me right in the ankle ball. Ooh, that turned purple. That felt good. Yeah. Anyway, so what happens then with arcs and circles and chords? If you have congruent circles, that means that the radii are always the same. Okay, two circles will only be congruent if and only if the radii are the same. And then if arcs are congruent, then their corresponding. If chords are congruent, then their corresponding arc lengths would be congruent. So if you're in the same circle or within two circles, if this distance and this distance are the same, then it means the distance here and the distance here has to be the same. Correct.
So is that if and only if? Remember chapter 2?
If and only if the line is congruent to this line.
It's a really, really easy thing to see.
Now, prove to
It's kind of a logical way of thinking, right? If the chords are congruent and their corresponding arcs are congruent, I can also say if the corresponding arcs are congruent, those arcs are congruent, their corresponding chords. If we go here.
Now, it's really, really easy to see how this works. You guys agree that these are both just 1 foot rulers?
What is one rule?
No, they're close enough.
one's clear.
So it's really easy to see this, is that if you've got a circle, trying to make it work works. If these two guys are the same distance, no matter where they're placed in the circle, those two arcs will wind up being the same.
Oh, yeah, because it's the circle.
Because they're in the same circle, so no matter where this goes, those two arcs that they're touching, they have to be the same. It doesn't matter where those chords themselves are placed in it, because as it goes through, this distance never changes, which means the distance on the curve will never change. And the reason that happens is because since this is always the same, if this is always the same, when I draw from the center, I don't know if this is going to work. Actually, we'll just do this. Yeah, the circle thing was getting all weird. So if this distance here is always going to be the same, when I draw from the center here, this is always the same, isn't it? So no matter where that goes, inside of that circle, no matter where it gets placed, this central angle will always be the same, which means that the arc that it hits will always be the same. And I don't know how well I can make this work, but if I rotate this, it might show a little bit. Let's see if this will work. Now, obviously, I'm trying to spin the circle. No, let's see if I can do it this way.
In a circle, it's still going to be a circle.
Let's do this. Oop, sorry. Oop. Now, if I can get this to work, this might work better. Sweet, slow. So no matter where this goes in the circle, sorry, I try to see a way to make it work. It just spins too fast. No matter where that goes, that arc will always stay the same. And the reason that happens is because isosceles.
I was gonna say, just looking at the clock. If the clock goes right now, bam, and the second it's not moving. And then the hour thing and the minute they start to spin. Is that what you're trying to do?
Yeah, but they spin in the same position.
Right.
Because if you remember that when you're in a circle, a chord just has endpoints on the circle. Radii will always go to those endpoints. You're always going to be able to create an isosceles triangle. Yes, sir.
A better example would have been with
Oh yeah, but remember with the compass, it's always become a semicircle with the north-south. That's it. But I see where you're going with that. I was trying to show with a smaller part without being that semicircle. Yeah, you are totally right on that one. I didn't think of that one, but that's a good idea. You guys understand what he means by a compass? On a compass, if you have a compass, you have your magnetic north, and usually what's right behind magnetic north is
I
south.
was actually talking about like instrument.
Oh, the circle thing?
Yeah.
Oh, yeah. I didn't think about, yeah, as we marked the arcs around. That's how we made that hexagon.
Yeah, that's the kind of compass I was talking about.
I thought you were talking compass because I was envisioning the straight across as it's going to rotate to magnetic north all the time.
No, but you are right with that.
What he's getting at is this, guys. Remember when we took a circle and we marked off with our compass and we connected something better than that, but we made all that. That's basically, and I think that's what you're getting at. Okay. That's the same basic idea here. When you get those congruent chords, and then all of those arcs are also congruent. That's why when we had a regular hexagon put in there, each of those chunks want to be 60 degrees because all the central angles had to be 60 degrees and so on and so on. That's a good one. I didn't think of that. Same thing goes here. When you have two congruent chords, it means you'll have congruent arcs. So if arc GH is 100 degrees, what's arc IJ? 100 degrees. What's your okay? So if that's 100 degrees, okay, let's make this an extra step then. So then what is angle G? What's angle G going to be?
That's 100. Okay. GH is 100.
Remember, it's an isosceles triangle. If you know arc GH is 100, what do you know about angle GKH?
It's 100.
It's 100.
So that's 100 degrees. It's an isosceles triangle. Now,
40.
Right. I was just
This is
about-
isosceles. Remember, guys, if your arc measure is 100 degrees, that means your central angle is 100 degrees. These are radii, which makes that isosceles, which makes these both congruent. They both have to be 40. Right? Notice there was about what? 4 different chapters worth of things right there? Nothing anything all that difficult, but you're going to have to remember bits and pieces from a lot of things throughout the school year here. Okay? That was a good question. It's a good one. Okay. Another one that's really, really easy is that if one chord is perpendicular to another, one of them has to be a perpendicular bisector, excuse me. One of them has to be a diameter. One of them has to be a diameter. And then going backwards out of that is if a diameter is a perpendicular to a chord, it bisects that chord. This is really, really, really easy to see how that has to work. Because remember, as you have this is a diameter. If that's a diameter, isn't a diameter a fancy name for a chord? The diameter is the fanciest of all chords. It's always going to be the longest chord within a circle. Okay? That diameter, no matter what, by rule, has to go through the center of the circle. As it goes through the center of the circle, it is at where it touches the endpoints of the circle, which means it's as long as it's going to get. And no matter what, if this is perpendicular here, as this rotates through, as it becomes perpendicular, then it has to be at the dead center of that chord. It can't be anywhere else. So since that becomes perpendicular, that's what you wind up with, the chord becoming bisected. Now, fair warning, you see a right angle, which means you're going to have what? Right triangles, because one of the things you'll be able to draw here that you'll see pretty often is right triangles out of that. You'll get right triangles, right angles. You'll be able to figure out distances here. You'll be able to figure out radii. You'll be able to do a whole bunch of stuff because of that. The idea is if a diameter bisects, or if one chord is the perpendicular bisector of another, one of them has to be a diameter. And again, as I said, if you go backwards with that, if a diameter bisects a chord, then it is perpendicular to the chord. Or if a diameter is perpendicular to a chord, it bisects it. It's kind of the verbiage on that. It's, like I said, it's not super difficult, but it is when you see it, you have to remember that you're going to get these bisects. Remember, when you bisect something, you cut it in half. Okay? Those two segments will be congruent. Now, the other thing that will happen is that since this part, the chord gets bisected, so does the arc. The arc gets bisected as well. Okay? So and then depending upon numbers and whatnot, you'll be able to figure out central angles, arc measures, lots of things out of this. Okay? And that's just a little subtle nuance there. If the chord is bisected, then that means that the arc has to be bisected. Okay?
Yeah, go on.
Same thing here. Same idea. This is also very easy to visualize. Chords of the same length, no matter what, have to be the same distance from the center. Because if you think about the curves, when you have a circle, when you have a chord, when this chord gets placed here so it touches both spots, if these two chords are of the same length, they have to be the same distance from the circle. Okay? They have to be the same distance from the circle. Chords that are in the same circle or within congruent circles, two chords are congruent if and only if they're the same distance from the center. You can say that backwards. If two chords are equidistant from the center, then the chords are congruent. It's very, very simple, but this just happens to kind of stink that there's a lot of words. Okay?
You may have to read those words. Sometimes the diagram is marked, other times I'll tell you the directions. Chord DE, segment DE is congruent to chord BC. And if you know that, then we know some other things. We know arc DE is going to be congruent to arc BC. We know that those two little pieces are going to be congruent. We're going to know that DF and FE are going to be the same distance because it's bisected.
Yep. And when you are equidistant to something, how do you measure distance?
With a ruler.
Okay. When you measure something with a ruler, if you wanted to measure how tall you are, we measure how tall you are on a diagonal or when you're standing straight up.
Straight up.
Which means that when you are measuring distance, this distance to here is always going to be,
Straight up.
or, how about that? All right. Remember, when you're measuring distances, you're always measuring the way distances are measured. They're measured in such a way so that there's always going to be that perpendicular distance. I'm not going to measure to that wall by going to the corner. I'm going to measure it straight at it because that's where it would be what we would call square. That's where all those terms come from. So as you get into these things, what we're going to be able to do is some very, very, very simple math. And for some of these, you probably won't, oops, sorry, that's really loud. For some of these, you probably won't have to draw it out because, as I said, some of the math here is pretty quick. We're just trying to find some measures here. Thank you. Yeah, the glare is just enough. So as I'm looking here, I'm just looking here. Are my chords congruent?
Yes.
Okay with that? They're both 18, so they have to be congruent. Are the chords perpendicular to the center, like with distance-wise? Okay, which means that if QC is 7, what is QA? There you go. By rule, if chords are congruent, they're equidistant from the center.
I didn't see that line.
What's the measure of segment DC?
Be 9, yeah, it would be 9. What would your radius be then? What'd you do? You have to find your radius. If you think about it, remember by the rule, this becomes 9, this becomes 9, and this much is 7. What do you do then to figure out your radius? Pythagorean theorem. We're building,
81.
we're just building
It's 10. Radius is 10.
AC, or AQ, excuse me, 7. What I'm showing is, what we're trying to show is that you can do so much out of one question. Because you've got, once you get right angles, Pythagorean theorem comes into play. So how do you figure out what the radius is?
So right now, that's 81.
Yep, 9 squared plus 7 squared is our radius squared. So that's what, 81 and 63?
It's 40.
Oh, 40, I'm sorry. I looked at the 8 times 7. Sorry about that. So that's what, 130? Square root of that then is, does it have a, okay. For some reason, yeah, because 4 doesn't go into it, so there you go. Okay. That's the idea, that you can build off of this problem real quick without too much craziness, because it's one little step on top of another little step that you can continue. We could figure out angles because you've got right triangles, which means you can use SOHCAHTOA. You can figure out arc length because you've got your radius. You can figure out central angles. You can do all of that stuff off of one little question here. Circles become, I'm starting to see why they put circles at the end, because it is all review of everything you've done second semester.
And some good application of the algebra that they're going
Yeah.
to be expected to know as soon as they get to next year.
Yeah, so I don't mind circles being last. Look
How
at me.
was it? How was it in the other book?
It was 10, then we went area spelling.
Oh, okay.
Yeah, it was weird.
All right. It's the one good thing about this book.
I gave you one compliment,
Yeah, I agree.
and that's all.
And that's all.
That's all you're gonna get, and you're gonna like it.
So we're gonna pretty much just be saying what's going on.
Excuse me. Yeah, it depends on the problem. For example, in this case, are arcs SR and TU going to be congruent? Why? They're not parallel. They're perpendicular and equidistant to the center, which means the chords have to be the same. So if one chord has an angle measure of 95, the other chord has to have an angle measure of 95. Okay. Again, same idea as we did earlier. If I know that the chord is 95, what's the central angle? 95. This whole angle here has to be 95, which makes both of these base angles how much?
85.
Well, you add them up, they'll add to 85, so what's half of 85?
42.1.
And that's kind of what you're going to be able to do, right, as you go through. Now, as we get going even further, no, I can't show it on this one. Never mind. You can also get to the algebra.